Hello friends, I welcome you in lecture number 5 on Laurent series. In this lecture also we will do two more problems on Laurent series. So we start with this example. Find the Laurent series representation of the function e raised to z divided by z minus 1 whole square with center z0 equal to 1. Specify the region of convergence of obtained Laurent series. So here our function is e raised to z divided by z minus 1 square, and we have to find out Laurent series with center z equal to 1. That means we have to find out Laurent series in powers of z minus 1. So first we have to decide the annular domain with center z equal to 1. So first we have to find out that in which annular domain our function is analytic. Now our function is e raised to z divided by z minus 1 whole square. We know that e raised to z is analytic at every point in the complex plane, and this z minus 1 whole square is also analytic at every point in the complex plane. But because z minus 1 is in the denominator is 0 if z equal to 1. So this whole function is not analytic if z equal to 1. So we have to exclude this point z equal to 1 at which our function is not analytic. So if we consider z equal to 1, so we don't have to consider z equal to 1, and if we consider any circle with center z equal to 1, then our function is analytic in this circle. So there is no restriction on the radius. If we consider any circle with center z equal to 1 and any positive radius r, and if we exclude the center, that is if we consider this condition, absolute value of z minus 1 positive, that means z minus 1 is never 0. This implies z is not equal to 1. So to exclude z equal to 1, we consider this condition, and there is no restriction on this upper bound, that is there is no restriction on the circle, on the radius of this circle. So we can see that our function is analytic in the domain 0 less than absolute value of z minus 1 less than infinity. So we can obtain Laurent series of our function in this domain. So first we consider let f of z is nothing but e raised to z divided by z minus 1 whole square. Then as we discussed, f of z is analytic in the domain, in the annular domain, which is given by 0 less than absolute value of z minus 1 less than infinite. So we can represent our function as a Laurent series in this domain. Now this z minus 1 square is already in powers of z, so we have to represent e raised to z in powers of z. So for that we rewrite e raised to z as, now f of z is e raised to z divided by z minus 1 whole square, and we rewrite this power z as z minus 1 plus 1, because we require our Laurent series in powers of z minus 1, and we keep this as it is. Now this is this can be rewritten as e raised to z minus 1 times e divided by z minus 1 whole square, and this we can again rewrite as e divided by z minus 1 whole square times e raised to z minus 1. Now we know the Maclaurin series expansion of e raised to z, we have already derived it. So we know that if we have e raised to z, then this e raised to z is analytic everywhere, and its Maclaurin series is given by 1 plus z square by 2 factorial plus z cube by 3 factorial and so on, and this is valid for all values of z. So this is valid for absolute value of z less than infinite. So using this series, we will consider we find out series for e raised to z minus 1 using this series. So instead of z, here we have z minus 1, so we will replace z minus 1, we will replace z by z minus 1 in the Maclaurin series expansion of e raised to z. So this 2 as it is, e divided by z minus 1 whole square, and now we replace z by z minus 1 in this series. So we have 1 plus z minus 1 plus z minus 1 whole square divided by 2 factorial plus z minus 1 whole cube divided by 3 factorial. If we wish, we can write one more step. Next step will be z minus 1 raised to 4 divided by 4 factorial. But this is valid, this expansion is valid in the annular domain 0 less than absolute value of z minus 1 less than infinite. Now we can rewrite this by multiplying with e over z minus 1 square, or we can keep e outside, and or we can multiply with e over z minus 1 square. So first term is e over z minus 1 square. We are multiplying each term of this series by e over z minus 1 square. So with 1 we have e over z minus 1 square. If we multiply this with this, 1 z minus 1 will cancel out, and we will have e divided by z minus 1. Then here z minus 1 square will cancel out if we multiply these two, and we will be having e divided by 2 factorial. Then we multiply with this, so we have e divided by 3 factorial, and this z minus 1 square will cancel out, so we have e divided by 3 factorial into z minus 1. And if we consider multiplication with this term, we have e divided by 4 factorial into z minus 1 square. And so on. We can imagine next term will be e divided by 5 factorial into z minus 1 cube, and so on. And this is valid in the open disk 0 less than absolute value of z minus 1 less than infinite. This is valid in this annular domain, not open disk. This is the annular domain with center z equal to 1. So this is the Laurent series expansion of given function, and it is valid in the in the annular domain 0 less than mod z minus 1 less than infinite. Okay, so we can write that region of convergence is 0 less than absolute value of z minus 1 less than infinite. That means this series on the right hand side converges to function f of z at all points except z equal to 1. So in this way we can obtain the Laurent series representation of this type of functions, and we can specify the region of convergence. So to decide the region of convergence, we have to decide at which points our function is not analytic, and we will exclude those points at which our function is not analytic. So now we consider one more problem. represent the function f of z equal to z plus 1 over z minus 1 by its Taylor series with center 0 and state where the representation is valid. Also we have to represent by its Laurent series in the domain 1 less than mod z less than infinite. So first we decide our function is not analytic at which point. So our function is z plus 1 over z minus 1, and this is rational function, division of two polynomials. So it is not analytic if z equal to 1. So our function is analytic at every point except z equal to 1. Now here we require Taylor series with center 0 and Laurent series in this domain. So center of both the series is z equal to 0, or we require both the series in powers of z. So we have to consider center at z equal to 0. So this is the center z equal to 0. Our function is not analytic at z equal to 1. So if we consider this circle with radius z equal to 1, then our function is not analytic at this point z equal to 1. So that means our function is analytic everywhere inside the circle. This is the circle mod z equal to 1, and function is not analytic at z equal to 1. Therefore, if we consider the set of all points inside the circle, then function is analytic in the open disk mod z less than 1. That means our function is analytic at every point in the open disk with center z equal to 0 and radius 1. This is open disk mod z less than 1. And we know that if our function is analytic in the open disk, then we can represent it by Taylor series. So here function is analytic in the open disk with center z equal to 0 and radius 1. Therefore we can represent our function as a Taylor series in this open disk. Now if we consider the set of all points outside the circle, that is if we consider absolute value of z greater than 1, then also our function is analytic at every point which is outside the circle. If we consider the set of all points outside the circle, then our function is analytic in this region or in this domain. So the set of all points outside the circle is given by absolute value of z greater than 1, and function is not analytic at z equal to 1 only. So function is analytic at every point outside the circle. So here there is no upper bound, we can write infinity. So this set of all points outside the circle is nothing but 1 less than absolute value of z less than infinity, or we can simply write absolute value of z is greater than 1. So our function is analytic in the open disk mod z less than 1. So in this open disk we can represent function as a Taylor series. Now our function is analytic in this annular domain. So in this domain we can represent our function as a Laurent series. So we will do both the sub parts one by one. So first we find out Taylor series with center 0, and we have already discussed that where the representation is valid. So representation is valid in the open disk mod z less than 1, because this function is analytic at every point in this open disk mod z less than 1. So before that we rewrite our function. Our function is not proper function. Here degree of numerator and denominator is same. So first we rewrite our function as, we can rewrite this 1 as 2 minus 1. So if we consider this z minus 1 over z minus 1, that is 1 plus 2 divided by z minus 1. Now first we consider the domain mod z less than 1, or first we write what we have discussed. F of z is analytic in the domains mod z less than 1 and 1 less than mod z less than infinity. Because function is not analytic at z equal to 1, we have these two domains which do not include z equal to 1. So first we find out Taylor series in the domain mod z less than 1. So for first part we consider Taylor series representation. So now first we write down Taylor series representation. Our function is f of z equal to, now we consider this 1 plus 2 over z minus 1. Now function is analytic in the open disk mod z less than 1. So we rewrite this z minus 1 as 1 minus z. We take negative sign outside. If we multiply with minus 1, we will have minus 1 plus z. Now if our function is analytic in the open disk mod z less than 1, so we can use that standard Maclaurin series expansion, which is 1 plus z square plus z cube and so on, and this is valid in the open disk mod z less than 1. So we are using that standard Maclaurin series expansion of 1 over 1 minus z, which is 1 plus z square plus z cube, and this is valid in the open disk mod z less than 1. And we have discussed that our function is analytic in the open disk mod z less than 1. So we can use this standard Maclaurin series expansion. Now we simplify this. So this is 1 minus 2 minus 2z minus 2z square minus 2z cube and so on. In the bracket we have to write down that it is valid if mod z less than 1. So this is minus 1 and all these things as it is, minus 2 z cube and so on. This is valid in the open disk mod z less than 1. So this is the Taylor series expansion of z plus 1 over z minus 1, which is valid in the open disk mod z less than 1. Now we consider second case, or we have just written number 2. So now here we consider Laurent series expansion or Laurent series representation. So in this case we consider that fact that f of z is analytic in the domain 1 less than mod z less than infinity. So 1 less than mod z, this gives me 1 over mod z is less than 1, because mod z is greater than 1, that means z is different from origin. So that means z is not equal to 0, so absolute value of z is non-zero, therefore we can divide with absolute value of z, and this we can rewrite as absolute value of 1 by z is less than 1. Now we try to represent in terms of Laurent series. Our function is 1 plus 2 over z minus 1, which we have simplified. So 1 plus 2 over z minus 1. Now here absolute value of 1 by z is less than 1. So we have to take z common here. If I take z common, I will have 1 minus, I have to divide by z. If I multiply with z, I will have z minus 1. So I rewrite z minus 1 as z times 1 minus z. You can multiply with z to confirm. If we multiply with z, we have z minus 1. So now we have 1 over 1 minus 1 by z, and absolute value of 1 by z is less than 1. So we can use that standard Maclaurin series expansion. So instead of z, we have 1 by z. So we write powers of 1 by z. 1 by z square plus 1 by z cube and so on. And this is possible because absolute value of 1 by z is less than 1, and we are using that standard Maclaurin series expansion. 1 over 1 minus z is given by 1 plus z square plus z cube, and this is valid if absolute value of z is less than 1. So here instead of z we have 1 by z, and absolute value of 1 by z is less than 1. Therefore we can use Maclaurin series expansion of 1 over 1 minus z by replacing z by 1 by z. So now we have to just rewrite all the terms. This we can rewrite as 1 plus 2 by z plus 2 by z into 1 by z, that is 2 by z square, 2 by z into 1 over z cube, that is 2 by z cube, and then 2 by z raised to 4, and so on. And this Laurent series is valid in the annular domain 1 less than absolute value of z less than infinity. Our function is z plus 1 over z minus 1. So this is the Laurent series representation of z plus 1 over z minus 1 in the domain 1 less than absolute value of z less than infinite. So all we have to decide is that in which domain our function is valid, and using the condition of that domain we have to write appropriately. So here absolute value of z is greater than 1, therefore we are dividing by mod z, and we obtain that absolute value of 1 by z is less than 1. So here to use this series we require absolute value of z less than 1. So whatever quantity we have in place of z, absolute value of that quantity must be less than 1 to use this Maclaurin series of 1 over 1 minus z. So in each example of Laurent series, whenever we are using this 1 over 1 minus z, we have to make sure that whatever we have in place of z, absolute value of that quantity must be less than 1, so that we can use this Maclaurin series expansion of 1 over 1 minus z. So this is all about today's session. I hope you like this lecture. Thank you very much.